Thanks, Daniel, for the very nice words. Today I'm very glad to be here. Today I'll talk about evaluating unlearning and memorization via compression. So this talk is based on two joint works with Pratyush, Avi, Ziko, and Zach at CMU. Okay, so let's cut to the chase. Why do we use compression? Well, there is a very long connection that people have established between prediction and compression. And because of the popularity of LLM recently, this connection has been sort of zoomed in and more people start to look at it. But essentially, giving a predictor and compressor, you can convert one to the other in a very handy way. In particular, if I give you a predictor which models the data distribution, you can essentially use that for coding, right? So let's imagine you have, let's just use language model as an example, which does next token prediction, and you're essentially modeling distribution over a sequence, and then you can use many compression algorithm to use that to actually reduce the number of bits to represent that string. For example, arithmetic coding nowadays is the go-to compression algorithm for ML practitioners. On the other hand, if I give you a compressor, you can construct by hand a predictive distribution that you use to do next token prediction based on the code length, right? So essentially, you're trying to look at how much information you get based on how much you can reduce the code. So this now you have this equivalence between predictors and compressors. So this makes it very, very natural to apply existing information theoretic tools for foundation model analysis. In this talk, we'll primarily focus on autoregressive language models. So we have this equivalence, and concretely, these generative models, they compress data to different extent based on how much they overfit, right? So there's actually nothing special about compression here. The compression here just means, how much you're generalizing to this data point, right? How confident you are about a certain point. If you're very, very confident about the next word, then you can compress the next word using very small number of bits. If you're not very sure, you're very uncertain about the next word, and then you probably need a lot more bits, right? So it's really just how you generalize or how you overfit to certain data. This property make it very natural to evaluate whether your model has unlearned some information or whether your language model has memorized some information, right? So I just used the word compression because we actually use this word in one of the work. So I try to unify both unlearning and memorization in this talk. But really, it's just how confident you are about certain prediction. So the first part of the talk, I'll be presenting our work named TOFU. It's a task of fictitious unlearning for language models. High level, it's evaluating unlearning based on the divergence between two model distributions. For this, we developed a robust evaluation measure, which we will go into detail. And in the end, we show that existing unlearning algorithm still need a lot of room for improvement. So to set a ground for the unlearning problem, LLM nowadays is trained on vast amount of data, which is very likely to contain anyone's private information. And when you prompt this language model, very specifically, it's able to spit out that piece of information. Unlearning here just means I want to forget about some person or any knowledge that someone deemed to be private or sensitive. Why should I care about this? First of all, there are ongoing regulations for this. In the European Union, there is GDPR. In US, there is another act called CCPA, which all say users have the right to be forgotten. And then whenever a user file this request, the model provider have to be compliant in some sense. Now, on the other hand, there is actually real danger for information leakage. One of the prior work discovered that if you prompt GPT in a very specific way, it's actually able to spit out some of its training data. And this this particular example is actually information about one real person. So what have people done previously for this? Previously, we mostly focused on classification models. And there's a rigorous definition of machine learning that's based on differential privacy. So we can stare at this definition a little bit. It says, for all data set S, and then I request to forget a subset U of S, a learning algorithm. So this definition is on an algorithm. The algorithm successfully unlearn if I unlearn U, right? So A hat is the unlearning, A bar is the unlearning algorithm. A of S is the learning algorithm that learn on S, and T of S is some statistics that's available to A bar, right? So you can imagine, T of S is, it could be the repetition of the data, and then A bar is, I'm simply relearn on that repetition. So I apply this unlearning algorithm. That's what happened on the left-hand side. On the right-hand side, I said, okay, now let's just relearn S without the forget set U. Right, so that's what the right-hand side says. Here, this symbol just says empty set. So they have some pedantic reasons why they want to apply this sort of definition, but really this thing says I'm gonna relearn without the set U. So now essentially the definition says, I apply my unlearning algorithm versus I learn from scratch, but without the forget set. These two models need to have very similar distribution, but then I'm really applying this algorithm and unlearning algorithm multiple times, right? So you can think about how you can actually test this. If you want to test two distributions are the same, you need to apply this randomness many, many times. So this makes unlearning very, very hard to audit. You essentially need to apply the same unlearning algorithm with different randomness a couple hundred times. And then you evaluate the difference on model distributions. So that's one approach that people have done before. The other one is more on the side of how you design the ML system. Right? So this side, the figure here basically says you can shard your training data in a very smart way. And then for every sharded data, you train the model, but at every certain step, you log down the checkpoints, right? So whenever you have this red part of the data you want to remove, you only need to retrain this part, and you only need to retrain from the checkpoint that has seen this data, right? So you only retrain part of the data set. But really, so this actually guarantees unlearning because the model here never see that data, but also it's like a very heuristic engineer effort. So overall, the Gaussian mechanism moment is not here yet. So for the privacy people, Gaussian mechanism is essentially you're injecting Gaussian noise to your training algorithm, which guaranteed differential privacy. It's very hard to enforce unlearning on the other hand. Well, actually, one thing I want to point out before is if the learning algorithm A is differentially private, then you need to do nothing for unlearning, right? So if A satisfies differential privacy, then it automatically satisfies the epsilon delta unlearning algorithm. So strictly speaking, unlearning is strictly easier than DP. A very good example is k-nearest neighbors. So to unlearn k-nearest neighbor, all you need to do is take out the private data in the database, and then you run inference, just like how you run the previous KNN. But that algorithm is nothing private, right? It exactly memorizes every single training data. So even though this notion is strictly easier than differential privacy, we do not have an algorithmic way to achieve this. So instead, we propose to look at a model-specific notion rather than algorithm-specific notion. So we're looking at one model, and then we ask whether that model is safe or not. So this is from another recent paper that also promote this kind of definition. It compares some sort of divergence between your model P and a safe model. So the safe model is basically a model that has not seen this private data X before. So now you can imagine, you unlearn some data, you get this distribution P, you compare this distribution to a safe distribution that has never seen that data before. You want them to be close. So, okay, so maybe it's all we need, right? But then there is this notion of predictive multiplicity, which essentially says, if I give you two competing models, they have very good performance. So two models have very similar performance on the test set, but they can still vary arbitrarily on any given data point. Here's a figure, right? So you're trying to classify the plus sign from the minus sign. If I draw you two lines, HA and HB, they all have perfect accuracy, but they will have actually opposite prediction for these two symbols. So this is coined as predictive multiplicity. The issue here is we can have multiple choice of safe model, right? So one of the safe model might be close to P. A different safe model might be far away from P. So it's really questionable, what is a good candidate for a safe model? And lastly, what is a divergence measure, right? I can construct any information theoretic divergence I want. There's KL divergence, there's GS divergence, but what is one that we actually need? And ideally that divergence measure should also be robust to randomness. So overall, previous attempt focused on classification models. There is DP style definition, which are very hard to arbitrate. We'll look at divergence style definition. But the question is, what is the right divergence and what is a good candidate for safe model? Okay, so before we dive into the evaluation metric, let me introduce to you what we construct in TOFU. It is essentially a synthetic data set with 4,000 QA pairs. Each question answer pair corresponds to a fictitious authors. And we allow users to have completely control over the data exposure. Right? You can forget any K% of the data that you want. So what's special about TOFU is it caters to contemporary generative model setting. It uses synthetic data. The model has not pre-trained on that. It simulates the fine-tuning stage, which makes it very fast and cheap to prototype your unlearning attempt. And we also have a robust evaluation. So this is how you actually use TOFU. You first fine-tune your model based on the pre-trained model on all the data. And then you forget K% of the data from the fine-tune model, which we call that set forget set. On the rest of the set, which we call return set, you again fine-tune a model from the pre-trained model. So that's the return model. And then we evaluate the forget model on the return set. So so in addition to the return set here, we also evaluate your model's knowledge on these two separate data sets, which contains knowledge about real authors and also several random facts about the world. And lastly, we compare the forget model and the return model on the forget set, right? So this is the part where we use this notion of divergence. Okay, so for model utility, we compute these three different notions. The first one is probability, which is very straightforward. We compute the probability of the true answer given the question. We compare the Roche score of your model's output to the ground truth answers. And then we compute the truth ratio. So for this, the truth ratio is the likelihood of a right answer to the likelihood of a wrong answer. If you're dealing with multiple choice question, this is actually very straightforward to think about what a truth ratio is. But what about QA pairs, right? So for the true answer, there's infinite number of ways you can express that. So what is a good right answer and what is a good wrong answer? And we'll talk about that in detail, I think, in the next slides. But so now we have three different statistics: the probability, Roche, and truth ratio. On these three data sets, we get nice statistics, and then we take the harmonic mean over them. Essentially, this gives you the property that if any of the statistic is low, then you have low model utility. Unlike if you just take the arithmetic mean, then one low statistic may not affect your overall model utility too much. Okay, so what is the truth ratio? Here's the sample question I answered from the TOEFL dataset. The true answer here is just a paraphrased version of the original answer. So you can see they have the same knowledge, but the expression is slightly different. And then the wrong answer is a perturbed version of the paraphrased answer. So the expression is the same as the paraphrased answer, but the knowledge here is actually wrong. Truth ratio is just the ratio between the log likelihood of the perturbed answer to the log likelihood of the paraphrased answer. So intuitively, this decouples how much your model overfits to the expression of this answer versus how much your model actually maintains knowledge within that sentence. To actually evaluate how well your model forget, we get two models: the unlearned model, where you apply the unlearned algorithm to, and we get the truth ratio of the retained models. So I get two sets of truth ratios, and then we compare their statistic out of Kolmogorov-Smirnov test. So the test statistic goes like this. I have two sets of truth ratio. I draw their CDF. I look at the maximum gap in this between these two CDFs. So if the gaps are very large, if the gap is very large, then they are significantly different, which gave you some evidence that you haven't unlearned successfully. If the gap is small, then you cannot distinguish between those two sets of distributions, then that suggests you sort of successfully unlearned.
Question?
So you may ask, yeah.
Is in the previous slide, the x-axis are the data points, as in like the instances from your TOEFL dataset?
So here, the x-axis will be the value of the truth ratios, right? So these two are CDFs. The CDF of truth ratio, which are just two sets of numbers, right? So the truth ratios, they are ratio between two log likelihood. They're actually not bounded.
I see. Okay. I see. Thank you.
Yeah. So you may ask, why do we choose this? Well, there are certain sanity checks that these divergence measurements should pass. Essentially, if I present you two models, both of them are trained on the same set, then they should have indistinguishable truth ratios on that set. If neither of them are trained on a data set, then they also should have indistinguishable measurement on that set. If one is trained on set data A, the other one is not trained on data A, then they should have distinguishable statistic on that set, right? So for example, the fine-tune model is trained on both the forget set and retain set. The retain model is only trained on the retain set. So these two models should have very similar truth ratio on the retain set, very different truth ratio on the forget set, right? So you can do this sort of combination for every two models on every two data sets. We actually run all of them, and then we find out that truth ratio is actually very robust to these variations. And here I'm presenting you three of them. So I'm taking two different model architectures. Both of them are trained on 90% of TOEFL dataset, right? So retain 90 means I train on 90%, the retain set has 90% of TOEFL fine-tuning dataset. Even though the model architecture is very different, their truth ratio is actually quite close.
Question.
You can, yeah.
You mentioned that like on TOEFL dataset, like user have like arbitrary data exposure ratio, I mean, which means like they can make like the forget set extremely small, right?
Yep.
I'm just wondering in that like extreme case, because that's more kind of similar to the real case where the model is pre-trained on like large pile of data, but like they only forget like probably like 1 or 2 data points. So in that extreme ratio, are those like statistical tests also hold significance?
So yes. So if you look at the truth ratio, they are also very, very close. Yeah, they are also very close.
I see. Yeah.
Although I do want to say that forgetting 1% of the data is actually quite easy, which is orthogonal to the question you asked, but it is a very easy task.
I see.
Cool. Right. So we also draw, we also have 90%, 95%, and 99%, and then they all, the sanity checks all pass. If you look at, right, so the second figure is I train Llama model twice, but evaluate their truth ratio on the forget set and the retain set. They're significantly different. The last figure shows if I learn 2 Llama model, one on 90% of the data, the other one learn 100% of the data, and then they also differ very much on the forget set. Cool. This is actually sort of surprising because somehow this robustness is quite interesting because you can imagine just probability they actually differ a lot.
Yeah, that's actually pretty surprising.
Yeah.
Thanks.
Yeah. And now we look at 4 different unlearning methods. The first one is gradient ascent, which essentially just says on my forget set, I want to increase my loss instead of decreasing. Gradient difference is I do gradient ascent on the forget set, and then I do gradient descent on the retain set. KL minimization is I do gradient ascent on the forget set. On the retain set, I want to be close to my fine-tune model in terms of KL divergence. And in the end, we look at preference optimization, which decrease loss on the retain set. And then on the forget set, I encourage the model to spit out, I don't know, instead of the true answer. So here's a 2-dimensional figure of model utility on the x-axis, forget quality on the y-axis. You can see that they all sort of work because the forget quality will increase eventually, but then all the model utility decrease way too much. So even this point, the model utility doesn't seem to drop that much. The model is still not very usable. Right? So this model actually forget quite amount of the knowledge in the world. And maybe another sort of orthogonal interesting finding is there is a gradient of forgetting, right? So the forget set, here we should probably focus on the Roach the most. The forget set is the set we want to forget. The retain set is the set in terms of proximity is the closest to the forget set, right? So both of these are knowledge of fictitious authors. Real authors is closer to the fictitious authors because they're both about authors, and then in the end, we have the furthest thing that's fact about other world, like what is the capital of France? Right? You can see that as forget going, my Roach score on forget set decreased first, and then the retain set Roach decreased second, and then you forget about real authors, and in the end, you forget about world facts, right? So there is the forgetting actually happens based on the proximity of that knowledge to the forget set. So that I think this sort of suggests that knowledge exists in different part or different directions of your weights, which I think is worth investigating. So the main takeaway here is we evaluate model unlearning based on divergence compared to a written model. We define this robust measurement, truth ratio, and then we passed several sanity checks, and then we show all existing unlearning methods have rather suboptimal performance. If you're interested in this, there is a recent paper called Negative Preference Optimization that seems to be achieving very good results. But I really think, with a static data set and a measurement, you can overfit to these measurements very easily. So it's questionable whether this state-of-the-art unlearning algorithm actually has other divergence tests, which I also think is an interesting direction to look at. So now let's look at a very similar, a very closely related topic, memorization. We look at memorization from a compression point of view. We define memorization via how much we can compress the data, and then we also show there are several sanity checks. Okay, so actually, memorization is very, very close to unlearning. But for unlearning, we try to unlearn some knowledge, right? You don't want your language model to spit out any private information, regardless of how that information is phrased. But memorization is sort of an easier task. Right? You could still spit out the same knowledge, but what really matters is the way that particular information is expressed. Right? You do not, for example, you can say anything about Harry Potter that you want, but you probably do not want to spit out, generate any particular paragraph in the book. So to give a story, there's a famous lawsuit going on between New York Times and OpenAI, where NYT basically sues GPT for exactly recite their articles. Here's a picture. You can see the red fonts are the overlapping content. So it's very clear that GPT, they memorized these New York articles. But really, whenever you define memorization, there is sort of a question, what if your prompt, you're not controlling a prompt, right? Imagine there is a really good chat model that follows instructions. You can say, repeat after me. And the language model is going to repeat that. Of course, this is not the prompt that New York Times used, but here is one of the questions you should ask yourself whenever you try to define something. So just having the output matching a piece of training data exactly is not sufficient to claim there is a copyright infringement because of the previous caveat that we came up with. So what is a good evidence, a strong evidence that look like? Well, we think it's a very strong evidence if the prompt is short and the output match the copyright data. So as before, there is a natural tendency to say, you infringe copyright because you exactly output something. But then the question is, LLM is so powerful, if you give enough compute, it's able to generate anything you want. So we frame this problem differently, and we think copyright infringement mitigation is about how much your language model memorized this data. So this leads to our definition of adversarial compression ratio. From now on, I'll just call that ACR. It's basically you measure the length of the copyright data, X, and then you divide that by the length of the shortest prompt that exactly regurgitated sample X under your language model. Of course, we're not the first one to define memorization. There are many, many prior work that define memorization, identify memorized text based on different statistic or definitions. But really, they all lie on this spectrum. So on this spectrum, there are so many definitions. On one side, here's a representative one that says, is there any input that can exactly elicit the output? On the other side, we have another definition that says, does the beginning of the copyright data elicit that exact match of the rest? And each of them have their own issues, right? So on the left side, we have this pathological example where the prompt actually include the output. So the definition is not preventing this pathological case from happening. On the right side, we have many hyperparameters that we need to tune, right? Let me, for example, if I give you the first 10 tokens of a sentence, you are not able to elicit. But if I give you the first 12 tokens, it suddenly become able to elicit that text. Does that mean your language model memorized this or not? So there are some questions that when you use this type of definition, you need to think about. So one side, we have no constraint on the prompt. The other one, we have heavy constraint on the prompts, and then we really need to think about how to choose the hyperparameters. And here we think ACR, adversarial compression, gave a reasonable constraint that we need to put on the prompt. So here's an example of how you use it. Let's say the target string is a famous quote from Shakespeare's play. I passed that thing through my compression engine, and then I found out that I only need 4 tokens to exactly regurgitate that target string, right? So now my ACR is pretty high, so we think it's memorized. Now, if this target string is very unique, it has 26 tokens, you found out you probably need 45 tokens to generate this. Then it has very low compression ratio. So in our definition, it's not memorized. Rigorously, we call a string is compressibly memorized if under the generative model, I'm able to find a strictly shorter prompt, X star, that generates Y under M. So now let's briefly look at how this compression engine actually works, right? So let's take a little bit detour and see how you can find this shortest prompt, which I think is interesting on itself, but here it really doesn't matter what optimization algorithm you use. There are 2 parts. The first, you need to search over the length of the prompt. And then the second step is once you fix the length, you need to find the prompt that exactly generates the target. So actually, both of them are surprisingly heuristic. For a fixed length token, if you want to do the discrete token optimization, we use this algorithm called GCG to find X, which is a very popular algorithm you use to do jailbreaking. Right? So imagine if I want your language model to respond to some harmful question, you can optimize over a fixed length suffix to that question, such that your language model is encouraged to say the word sure, condition on that question, and the suffix. And after the language model spit out the word sure, it has this tendency to continually answer that harmful question. Right? So that's the step. That's the step you need to do for jailbreaking using GCG. Here we're almost doing that, but instead of saying sure, we're trying to let the language model to say exactly a target, which is actually a little bit harder than just jailbreaking. So the heuristic here is the algorithm for the heuristic search over the length. Right? So it's very easy. We just set a starting point of the length, and whenever we're able to find Z that exactly generates Y, we will decrease the length. Right? So Z has length N, and whenever this succeed, we decrease the length, and then we rerun this algorithm. Whenever we didn't succeed, we increase the length by 5. So there's nothing really. It's not something we test very thoroughly, but this seems to work pretty well.
Question?
Yes.
Are we searching in discrete space or continuous space?
Yeah. So this is searching over the length. So we are saying, okay, I'm gonna check any prompt of length 5.
Yes. So I guess my question was more like when you say when I search for a prompt, is this a discrete search? I think you don't show it here, but is this the prompt search is over continuous space or in space?
It's discrete.
Okay, thank you.
So this is the actual GCG algorithm that we use. So I think, okay, so let's probably go over this line by line. So we start with the embedding matrix to be E, and then we run this algorithm multiple times. N token is the number of tokens we have the freedom to optimize over, right? So for each of them, I look at the gradient of the loss of my target Y, condition on X. So X are the initialization point where I optimize over, right? So in reality, we randomly initialized these suffix or these free tokens that we can optimize over, right? So you're essentially just compute the gradient with respect to these free tokens. And then I'm picking top K based on the negative gradient, right? So it's like a one-dimensional, it's the first order approximation to how much I can keep decreasing my loss by going into that direction, right? So for every token, every free position, I pick the top K. Usually we pick K to be 250. And I'm sampling B number of batches, right? So for every individual item in that batch, I take X. So X is the previous initialization for this round of search. For every position, I look at the candidate and I uniformly take an item in that bag of tokens, right? So it is some sort of random search, right? But the random search has a candidate that have large gradient. So after I do capital B number of candidates, I pick the one that minimize my target Y, condition on that candidate. Now I start my second round of the search. But really, it doesn't matter. You can use whatever discrete search algorithm you want. It turns out if you just do random search, it's also going to work pretty well. So here, you're not even taking gradient. You're uniformly sampled within the vocab. That's the only difference. Here, I'm randomly sampled from the whole vocabulary. Here, I'm uniformly sampling from the top K largest token, the top K token with the largest gradient. And both of them will work in this case. So now, we can define whatever thing we want, but to make it useful, you need to show it passed the sanity check. The first sanity check, which, yes. Is there another question?
Yes. So it seems like in none of these algorithms, you care about fluency. So you just want a prompt that consists of a bunch of vocabulary to generate a candidate, a target copyrighted text. Basically, we are checking if we can generate that.
Yep.
And I'm wondering, what's your rationale for ignoring fluency?
Yeah. So here, when we consider, here we're really targeting from the information content perspective, right? So I'm saying I can find a prompt that has a smaller amount of information than the output. Here, information is measured in the length tokens. But I can't imagine, if you find a coherent natural language that exactly generate this. I can see values in that. But how do you define memorization based on that?
I guess the thing that I'm concerned is that we might be overestimating the memorization in this way, because by opening myself to prompts that are not fluent, it's just jumbled words, I might consider certain things. I might be able to generate things that are not necessarily memorized, and the only reason that I'm able to generate them is because I'm and I'm allowing my prompts to be non-fluent. So basically, I guess I feel like this might require, perhaps you already have it. It might require additional study to show that indeed, by without the fluency constraint, I'm not going to overestimate my memorization.
Right. So that is a concern. And I try to persuade you based on the sanity check that we run. So in fact, we are never able to find a string that is not in the training data that has high ACR.
As in, I see. So, sorry, one more clarification. In the algorithms that you search, the target string is part of the loss, right? So, like when I'm computing this loss is aware of the target string, right?
Yes.
Okay.
Yep.
So are you saying that if I just conjure up a string that I know for a reason that my language model has never seen it in the pre-training data, this
Yep.
algorithm is very unlikely that would be able to identify that. I would identify a prompt that would reconstruct that made up continuation.
Given that the length of X is no bigger than the length of Y.
Got it. Thank you. Yes, that would certainly convince me.
Right. So that's a very good sanity check to run. But the first one we check is whether bigger models memorize more, and then we look at several different types of strings that are memorized, and then in the end we can look at how hackable this thing is. So there's nothing special about this. As model size increase, I have more data being memorized. And the data here are famous quotes that show up in the training data multiple times. So there is a natural tendency that more with small parameters, you memorize more. And then we look at 4 different types of strings and see whether they're memorized. The first one is famous strings that show up in the training data multiple times. And then we look at random strings. So these are actually random token that's not natural language. They should never be memorized. And then we look at natural language that's guaranteed to not exist in the training data. So these are recent news articles that released after the model is trained. So these are the data that should also not be memorized. And in the end, we also look at the training samples that exist in the training data, but they don't show up too often. So these are random sentences from Wikipedia articles. Some of the samples may be memorized. So here's, I think it's a very good result that says 50% of the famous quotes are memorized. Less than 10% of the Wikipedia sentences are memorized. The recent AP News article, none of them are memorized. And random tokens are not memorized either. Right, so Daniel, I hope that clarified the question you have.
It did. Thank you.
Yeah, I do think, so to also clarify this, I think there is a confounder of how well your optimizer is. So it's very, very, it's likely that you're able to find a shorter prompt with a really good optimizer. But we just don't have that, which could also be an interesting thing to think about. So okay, so now let's look at what are some ways to hack this test.
Question. I have a question here.
Yep.
Can you go to? So it might be a bit long. Can you scroll back to the definition of like the ACR here? So this is defined as the argument of the prompt. So the minimum length of the prompt that you can elicit the model to generate a certain string. But in practice, you are not searching over the full set of prompts. So this is not technically argument. In practice, you're just searching for a finite.
Yes.
If I understand correctly. So have you considered some other notions of memorization here instead of making the model elicit to spit out directly the prompt the continuation Y? You use a threshold on the perplexity. So you say, okay, I have a fixed length of prompt, what is the lowest perplexity I can achieve? Like you search over X, and what is the lowest perplexity? If it's lower than a certain perplexity, then we say it is memorized. Have you considered this kind of memorization other than splitting it in a discrete way? Have you considered a continuous perspective
Yeah.
memorization?
So that's a very good question. For perplexity, I think the issue. So there are two concerns I have with perplexity. The first one is it's very sensitive to hyperparameter choice, right? So imagine you're computing perplexity, but you're changing the temperature of your language model. Now your perplexity change, but that shouldn't affect how much your model memorized. And
I think changing the temperature does change how the model memorizes. Like in a extreme case, if you change the temperature to 0, this becomes greedy decoding.
yeah,
And it actually alters the behavior of the language model significantly, I would say.
right. So here right.
Okay.
So here we're always using greedy decoding, right? So m of x equal to y. You're always greedily decode. You change
Okay.
your temperature, you change the confidence, but that really doesn't change how your model greedy decode.
I think what I'm saying is that if you change the temperature, if you use something other than greedy decoding, it changes the memorization behavior of the model, I would say.
Oh, so here when I say temperature, I just mean you take your logits and then divide it by a temperature tau, right? And then you use that as the logits for distribution. So that based on how large your tau is, your perplexity will change, right?
That's true.
But your model's memorization is not affected because your model weights are intact.
Okay. Maybe we can talk about this afterwards. So because I feel like if you alter the output distribution, you're still altering the model's memorization behavior. But we can talk about that later, I think.
Not about, right. So depends on how you sample. If you always sample in the greedy way, it doesn't really change. So your
Yeah.
model will still generate the same thing, but you're not confident. And then, okay, and then maybe another question, another concern I have with regard to perplexity is now you need to pick the threshold, right?
Yeah,
Like
yeah.
I do not know how to pick that threshold without training data.
Okay.
So that's one thing. That's one thing special about memorization because it's not membership inference. You know exactly what thing exists in your training set, but it's very hard to tell which one is memorized. Yeah.
Okay. Thank you for the explanation.
Okay, so here is an example of how you can do in-context unlearning and how is that just an illusion of compliance, right? So if you take this check model and then you optimize this suffix, it's gonna give you this famous quote. Now you just add a system prompt that, on its surface, it seems to give you this unlearning behavior, which says abstain from giving any famous quote. And then it's gonna say, I apologize, I cannot provide you this. But it turns out you can still optimize even with the system prompts. You can optimize over just 2 or 3 tokens to still exactly elicit the same target string. Right? So if you just do this system prompt level unlearning, it's not actually doing you any favor. And quickly we'll look at, if I take a model that's learned on tofu, I apply gradient ascent for a dozen of steps. As you gradient ascent, you're not generating the ground truth anymore. However, the compression, based on compression, you're still memorizing lots of the data. So I think I'm going to skip this small part. Essentially, it is about Harry Potter, how you can unlearn Harry Potter. There's another unlearn paper on this. But the moral of the story is, even if you take their forget model that allegedly forget about Harry Potter, you can still recover a significant amount of data from the novel that it's still memorized. And then if you paraphrase the famous quote, the average ACR actually dropped significantly. Right? So it really just captures, it's not capturing the semantic meaning of the target. It's capturing the target verbatim. So that being said, there are cases that are very interesting, and there are gray areas which I don't really have good answers to, but it's very interesting to think about, right? For example, there exist responses that's very long, but then they have very short generating function, right? So if you think about algorithmic information theory, it just means I have target that has very low Kolmogorov complexity. But then, you know, whether your model is able to compress this super long response doesn't seem to give you a good idea of whether your model actually memorizes or not, right? Your model could just be really good at counting. So that's one of the edge cases that I probably don't have a very good answer at this point. But perhaps for the argument, for our argument, response of this type is also in a gray area that we don't care about for copyright infringement, because it's very unlikely for copyrighted data to have a very short generating function. But maybe a more concerning issue is if you're a very skillful adversary, you can compress by yourself. So this is an example of flooring. After we posted about our work on Twitter, you can look at AP article on that day, which OpenAI has not trained GPT on. He was able to he construct by hand a compressed version of this article, right? He come up with this by himself. I don't know how he achieved this, but then this input has shorter length than the output. So this actually brings up an alternative definition, which Daniel has asked about. Here, we're not comparing ACR to 1 anymore. We compare that to a sample-specific threshold tau. Right? So before, we always set tau to be 1. But then, you know, obviously, there are data that's compressible by an adversary. Now it turns out maybe tau should be some other compression rate under a different compression algorithm. So you can think about ACR as compressing the output into a shorter length, but I can really compress Y using any compression algorithm I want. So here we just use the compression ratio under gzip. Okay, so now if you compare to gzip, it's actually successful in this case, right? So the Florence compression ratio is 1.2, but actually gzip is able to compress this into 1.7. So, you know, sometimes you need to pick a harder threshold to identify memorization. So the main takeaway here is we consider the copyright infringement problem based on memorization. We show that memorized data should be very easily compressible, and then here compression is measured in terms of token length. So I think this figure is not very interesting to me. It just shows you, what type of strings are marked as memorized when tau equals 1, and these are the strings that's marked as memorized when tau equal to a compression ratio under another algorithm. So I'll wrap up my presentation there, and thank you for attending.